I'm sure we'll learn many exciting things that are similar to what we've learned for the last two lectures. Rohini, please go ahead.
Okay, thank you very much. I hope you can hear me. Good afternoon to you and good morning to me. So now I just wanted to put here, which I was kind of happy to see, that this is the first lecture when I put the program for the 3 lectures, and everything that is bold is actually written on the transparencies then and has been covered in some form or the other. So looks like we covered most of the topics in lecture 1 and 2, except the precision testing of the tree level prediction is something that I had hoped I would cover in lecture 2, but which is what we are going to come to. So that is the part that is left. But in the third lecture, we really want to take the story of how standard model predicted existence and the mass of the new particles in terms of the previous experimental results, and how, it was a sort of race between experiments and theory. I would not say race, but more a very symbiotic relationship, which moved and propelled the standard model and the development of the final structure more and more. So there are 4 issues that I want to touch upon in today's lecture are the radiative corrections in a spontaneously broken gauge theory. What does it mean? Then oblique corrections and precision testing of the SM. Then how that led to the indirect determination or indirect prediction for the mass of the top and the Higgs. Then I also want to say a little bit about pure theoretical bounds on the Higgs mass that existed much before all this happened. And then the implications of the measured mass of the Higgs for the standard model. That was something that was related to a question that was asked to me yesterday at the end of the discussion. I may not be able to cover the last 2 points in detail, but I think it will be enough to whet your appetite that those are also very interesting questions that right now theory is really asking. Before even I begin my next slide, I should also say, or maybe I will clarify on an answer to that I gave yesterday in the discussions. Maybe, but I will move it to the end of the lecture because right now maybe better to get started. So let me begin by the summary of the physics ideas that we got in the first 2 lectures. So that at least this is what I wanted to convey. We understood what were the reasons which led people to believe that the weak interactions could be described as a gauge theory. Then the need for a partial symmetry. This was Glashow's name. Actually, it is the name of his paper. That is that a symmetry group of electroweak unification cannot be a simple gauge group. It has to be a semi-simple gauge group. Then the need of the spontaneous symmetry breaking and the content of the standard model with just a doublet Higgs that we constructed. And one of the most important prediction of that doublet Higgs was that the neutral current and the charge current effective interactions will actually be equal strength. Other thing we noticed that the standard model predicts masses of all the bosons in terms of just 2 parameters, sin theta w and lambda. Lambda was disconnected with the all the other particles. It only determined the mass of the Higgs boson. And the mass of the W and the Z critically dependent on the Higgs representation that has been used for the spontaneous symmetry breaking. But the fact that everything was a function of a single parameter theta W was very important because the couplings of all the fermions to the gauge bosons were actually determined by the representation to which they belong, and therefore they are universal across all generations. This is by construction. Then masses of the, and that is by the virtue of the gauge field theories. And all the fermions had to belong, all the fermions of a given charge had to belong to the same representation of the gauge group. And that came from the famous story requirement that the FCNC, flavor changing neutral currents, should be suppressed in the standard model. That is how standard model could automatically suppress them. And that was an experimental observation. The masses of the fermions needed arbitrary Yukawa couplings. then there is enough freedom in the mass generation mechanism of quarks to allow for accommodating the experimentally observed intergenerational mixing. It is not something that is forced upon us by theoretical considerations, but we have the freedom, and it was something that was useful because experimentally intergenerational mixing in the quark sector was observed. This mixing was only in the charge current sector, that in the charge current in the quark sector. And as I said already, while discussing point 5, that it's suppression of the flavor changing neutral current processes and the absence of flavor changing neutral current at the tree level could be avoided by making sure that the representation structure is repeated across the generations. That is, a charge of a given electromagnetic fermion of a given electromagnetic charge belongs to exactly the same representation of the SU2L cross U. Then in the last part of the lecture, we actually covered a bit in a rushed manner that the observed separation of the FCNC led to the postulation of the charm quark, and the separation beyond the loop level was actually explained by Glashow, Iliopoulos, and Mayani in the 4 quark picture, and MC was predicted. I would like to actually point out that the epochal paper, which predicted the mass of charm quark, one of them was a very famous Korean physicist, since this is happening in Korea, Benjamin Lee, along with Mary K. Gaia. And the observation of J psi then gave us the proof of gauge theory of weak interactions. The necessity of 3 generations of quarks actually was there to accommodate observed CP violation in terms of the quark mixing. You will be discussing that in the flavor physics course. And the existence of the same number of generations of leptons and quarks is required by the anomaly cancellation. So, and the rate of Higgs production, this is something I have not covered, but I want to convey to you that the rate of Higgs production in gluon-gluon fusion channel at the Large Hadron Collider actually rules out the existence of a sequential 4th generation of chiral quarks, which will get its mass via spontaneous symmetry breaking. So in short, we have seen all the generations of fermions that can get mass from spontaneous symmetry breaking in the standard model. So I have not discussed this part, but I thought that logically I should tell you that this is where this entire logical discussion will end. So now, after having summarized this, let me go back to where we had stopped yesterday. We yesterday saw how the electroweak unification was confirmed by the neutrino scattering experiments, neutrinos on electrons, neutrinos on muons, and neutrinos on nuclei, which was the major workhorse of the experiments in those days. After that, we also saw how the W and the Z were actually, we didn't see, I mean, I didn't discuss that, but how the determination of the masses of the W and the Z, that agreement of the MW and MZ, predicted from the single parameter that was determined from the neutrino current experiments, indeed supported the correctness of the standard model. And Glashow, Iliopoulos, Mayani, as well as our friends Rubia and Vandermeer got the Nobel Prizes for that. But there is something now, where did our enormous belief in standard model, there is no other group structure, that there is no other slight addition of another group, some other small Higgs representation. This really came from this wonderful experiment at CERN in the Large Electron Positron Collider. This is E plus E minus going to hadrons. And this experiment, actually, there were different experiments which were covered. We already met yesterday Pep and Petra, which gave us the initial confirmation or of the viability of the standard model by helping determine a unique value of sine square theta W. Then Tristan also I mentioned. And here you see that we were at root S of 60 GeV, much less than the Z mass. You are looking at E plus E minus going to hadrons. But the effect of this fact that there existed a Z resonance somewhere in the future actually showed up in the presence of this rising behavior. And that was like the shadow of this resonance, which was seen here. And that's what helped confirm people further that yes, Z actually, or some guy, heavy guy must also exist. And indeed, this is this beautiful determination. And now you see that this entire E plus E minus going to hadron cross section all the way up to the left two energies was actually completely, this solid line is the standard model fit. That means you keep the parameters of the standard model, which is only one, as you remember, G mu alpha and sine square theta W. Keep it free if you like and make a fit to the standard model. And then you see that the data actually were beautifully explained by the standard model prediction. Here, if you didn't include the large electromagnetic and QCD radiative corrections, this beautiful agreement will simply not have been there. And in fact, this entire story is a long story of high precision calculations. Please note here also that the E plus E minus going to W plus W minus cross section is this line. And I'm going to now focus on this line a little bit more. But what I really want to show you here is that the Z and the Ws, which were directly discovered at the P-bar P collider at both CERN and Tevatron, were here produced in large numbers, and you produce millions of Z. Now, what was the advantage of that millions of Z is what we are going to see in the next few slides. These are the high precision measurements, precision electroweak fits. This is the point that I want to come to. But before I discuss that, let me discuss this E plus E minus going to W plus W minus cross section, because it teaches us something very interesting, and it gives me the time to touch upon the two slides that I did not cover in my first lecture. But this is the data itself will tell you what the point I wanted to make then. So this is E plus E minus going to W plus W minus, just the total cross section. And what you see here is, of course, first the green and also the red line. These are predictions of the standard model. And these are the data. And as you see, the data are actually very beautifully lying on the standard model prediction. So you say, aha, standard model is confirmed. But what is the special feature of this confirmation? Because believe me, this slide is absolutely one of the first direct establishment of the ZWW coupling. And as you see here, this dashed line is if you include only the T-channel neutrino exchange diagram, and the cross-section continues to rise here. So now this is basically relating to the unitarity violation that we discussed very early, that here this is indicating a lack of unitarity in the calculate process E plus E minus going to W plus W minus. At very high energy, the cross-section will violate unitarity. But then you also know that T-channel diagram is not the only diagram. You add the S-channel, the annihilation diagram, E plus E minus going to photon, going to W plus W minus. Then the high energy behavior is somewhat tamed, but this still rises uncontrollably. Only when you add E plus E minus going to Z to W plus W minus diagram, the standard model prediction comes down to this green line, as well as the red line. And it is these that tells you that the triple gauge boson coupling, ZWW, tames the bad high energy behavior of the cross section, which is caused by the T-channel diagram. So there are two things. One is that it's a direct proof for the ZWW coupling. I will, again, if time is left, comment on the early work which people had done way, way before in 1974 or 75, where they had actually shown this fact theoretically. So I'll come back to that later. But this is a beautiful demonstration of the existence of the ZWW coupling and confirming to us that it is exactly what the standard model needed. And remember, the gauge coupling, self-couplings of the gauge bosons are determined exactly by the group structure. So this is the direct prediction, a direct confirmation that the standard model gauge group is SU2L cross U1Y. Not that anybody doubted this in after the precision measurement on the Z pole, but it is beautiful to see a real demonstration, and also this particular fact that how, if we did not know about the Z exchange, we would have, got complete no agreement at all. Now, this is something that you may not have seen. This is one experiment that perhaps people even have forgotten, but this is another beautiful proof of the verification of the electroweak theory. And this is from the experiment called HERA at DAISY. This is the electron-proton collider, which stopped working in 1995 maybe. And what this does is that this compares in the deep inelastic scattering cross-sections for two processes. Electron plus proton going to electrons plus X. So therefore, if you sit there and draw a diagram, I should have done that, but I haven't done it. A diagram, a Feynman diagram, you will see that it corresponds to an electron emitting a Z or the gamma in the T channel going on its merry way. And the Z or the gamma interacts with the proton and produces, this is the deep inelastic scattering. So it is the sum of the photon and the Z exchange in the T channel. And the charge current is nothing but the electron plus proton going to neutrino plus X, which is the W exchange. This is a rather difficult experiment at HERA to do. It's a collider environment, but I think they did a very good job. And what you see here in the red are the electron-proton charge current data. What you see here in the blue are the electron-proton neutral current data. And what you see is that the charge current data and the neutral current data actually merge around Q square of about 90 GeV square, which is where the, around the Z boson mass, where when both the exchange being particles being exchanged are sort of the same mass, then you see actually this electroweak unification really happening. I personally find this is also a wonderful sort of confirmation of unification. Now, in making all these comparisons, we had used the tree-level expressions for all the quantities. That is, MW was given by G2V by 2, and MZ was given by MW over cosine theta W, and so on and so forth. Now, clearly, in a field theory, all of us know that tree-level relation is going to change due to quantum corrections. Now, what we need renormalizability for is that it guarantees that these corrections are finite. And this renormalizability, in turn, is guaranteed by gauge invariance, and that, in turn, is guaranteed by the spontaneous symmetry breaking or the Higgs boson. So after, these things happened, after this thing happened, the order of the day actually was that now look for that Higgs directly, because you have already used actually the loop corrections in many of these tests. So therefore, that was first point. And second one, then that is the second point, that can you actually precision test standard model through measuring? Now, here is one thing to say that the agreement would not have been there if I didn't include the loop effects. But what was the difference? What was the discrepancy? What was the size of these loop effects on the observables? And do they really confirm the predictions of the standard model? So this is really what precision testing did. So let me begin with the simplest correction to the standard model predictions. We had MW equal to G2V by 2. But of course, as I said, there are loop corrections. But now immediately there is a difference between the W and the Z. W has charge current interactions and Z has neutral current interactions. So the loop correction which comes from for the W, for example, it's also clear to see that the heaviest fermions actually will make the largest contribution. There is a reason for that, but I will not be able to go into it just now. So there is this W, which is the major contribution is coming from TB bar, whereas for the Z, the contribution is coming from BB bar or TT bar. So which means that the size of the correction for the W and the Z at the tree level is different. Therefore, now if I calculate corrected masses of the W and the Z, and I calculate MW square over MZ square cosine square theta W, then actually you find that the corrected value of rho is slightly different from 1, and that is 1 plus delta rho. And this delta rho actually happens to be GF times MT square over 8 pi square root 2. Now remember, GF is extremely small. It is 1.01 into 10 to the minus 5 in units of proton mass square. So it is now enhanced by MT over MP. All the other mass contributions from all the other quarks are extremely small, and you can forget it. And only because the top actually has the large mass that it has, you actually have a contribution to rho, delta rho, of about 0.01 from this radiative correction. That is the point. So that's what I have written here, that the corrections for the Z and the W are different. The dominant corrections come from the loop containing the heaviest quarks T and B, and subdominant corrections actually also come from the Higgs. Because remember, W has a HWW coupling. So I can have W coming in, a W here, a Higgs here, and a W again. And that loop actually contributes only in dependent logarithmically on the Higgs mass. And this is actually proved by Veltman by something called a screening theorem, that the Higgs contributions to these masses will always be only logarithmic dependence on MH. Again, as I said, there are sort of very deep theoretical points why this happens, and we neither have the time and all the wherewithal to understand it. But I will, for those who are interested, I will only tell you that this is really coming from the fact that the W and the Z for the longitudinal degrees of freedom, the coupling to the fermions is actually for the longitudinal Z, it's dominated by this longitudinal degree of freedom, and it is the dependent, it is really the coupling that is proportional to the mass of the fermion that's making its presence felt. So this is really happening. This MF square dependency is really happening because of the Higgs mechanism itself, that the W and the Z get their masses from the Higgs mechanism. In addition to changing the W and the Z masses, another important correction is in the Z2 the Z2 to the vertex, which is coupling of the Z to a pair of fermions. I should have drawn it the other way around. Okay. And these three are what are called non-decoupling corrections. That means that even when the circulating fermion has a very large mass, they are not decoupling, and they will keep their presence felt at the low energies. And these are the so-called oblique parameters that exist. So now what actually happened was that before the top quark was found, since the delta rho depends on empty square, the measurement of rho indirectly gave an estimate for the top quark mass. Now these corrections, let me again remind you that the corrections can be calculated only if theory is renormalizable. Renormalizability was proved by Tauf and Veltman that endowed the calculability and predictability. And the precision measurements at the LEP1 of the Z properties, all the neutral current couplings, and the precision measurements of the properties of the W at the LEP200. What I mean by properties of the W? I mean the mass of the W, I mean the width of the W, for the Z, I mean the width of the Z. And these tests, and this is what we will look on the next slide, these tests at the loop level of all the relations of the couplings that were predicted by the standard model, corrected by loops like this, at least keeping into account the non-decoupling corrections. If these tests actually indicated a finite mass for the Higgs in the fields, then you would say that indeed this is an indirect proof for the Higgs, and hence an indirect proof for renormalizability, and hence indirect proof for the standard model construction. So this was the story. But to be able to do that, you needed high precision measurements, but you also needed high precision calculations. You needed higher order QED and QCD corrections, and they were completely non-trivial in size. Very importantly, good understanding of QCD was required to calculate correctly what the detectors observe in hadronic finer states, namely the jets. And extensive collaborative studies between the experimentalists and theorists actually produced a large number of LEP yellow reports, from which, to which some of us contributed, and some of us, and some parts we studied as young postdocs, as getting together the knowledge of the group of high energy physicists together. And this is actually, I would say, the beginning of what we see as snow mass studies and so on and so forth. These were the early studies of that kind. So what happened in the Z measurements at LEP1, where there were millions of Z's, literally, And when measured the width of the Z, the different branching ratios of the Z in different final states. And you know what I've done here is I showed you yesterday from 1983 a plot where E plus E minus going to mu plus mu minus and also neutrino experiments had determined value of GA and GV. Except what has happened is that I have this plot actually rotates GV and GA through 90 degrees. So this looks slightly different, but it is the same plot, believe me. This is nu mu bar going to E minus ellipse. This is nu E bar going to E minus ellipse. Nu mu bar E minus neutral current and charge current ellipses. This is nu mu E minus ellipse again. And then this is the E plus E minus mu plus mu minus symmetry, which now you see has shrunk in the size from that big last time what we saw, that it was a big blob like this here. And indeed, that is now completely changed. And if I took with now the one black point that I had shown you, 2 black points, where all the different ellipses sort of intersect. Now this intersection, if I just blew it up, and you see how narrow is the region of intersection, the accuracy of your GV and GA measurement, please look at the scale here. This is 0.041, this is 0.038, this is 0.035. So you see now that it is drawn on an entirely different scale, and GV and GA have been now super accurately determined, and therefore the prediction of MZ and MW is now super accurate. Now, what is the point of this? Let's understand that. Okay. So what we did now, what one does is that no longer one determines sine square theta W. Okay. Because now what has happened is that you have a whole lot of measured quantities. What do you have? You have MZ, you have gamma Z, you have total cross section into hadrons, sigma E plus E minus going to hadrons at a E plus E minus machine. This is the ratio of the cross section in a particular final state at the Z pole to the hadron production. This is the forward backward asymmetry, which we met yesterday. Then there is also, just like you have forward backward asymmetry in the production of the fermions, you can also have forward polarization asymmetry of the produced fermion. And in case of tau, you can actually measure the polarization. Then this is the ratio at E plus E minus going to BB bar to the E plus E minus going to mu plus mu minus. Then these are forward backward asymmetries into individual channels, so on and so forth. Then this is a very important quantity called forward asymmetry, polarization asymmetry at SLD. And of course, for the leptonic channel, you still extract sine square theta W. That is done, and that is here. Then MW you measured at LEP2, gamma W you measured at LEP2 again, and MT, the measurement came at that time from Tevatron. There was no LHC measurement, good LHC measurement at that time. And now what you see is that you take all these measurements, okay, and you have only one, how many parameters do you have to determine? So now let's understand first, before I say this, we will come back to this, what is meant by this. But what I want to show you here is that what you do is that these are all the measurements. These are all the measurements. Look at the accuracy of the measurement. The Z mass, for example, is determined correct. The error is here. And you have been discussing in statistical discussions, what does this small error really mean? So indeed, you have these high precision measurements. So now what do you do? The logical steps in your precision testing of the standard model is that we started with 3 parameters. Remember yesterday's first transparency, G1, G2, and V. Now, all the standard model couplings, gauge boson masses, are functions of these. We have seen that. And a large number of these electroweak observables have been determined terribly accurately at the thanks to LEP, thanks to SLD, and thanks to LEP2. Now, instead of using G1, G2, and V as the free parameters, let's say that let's use the parameters that we have measured most accurately and trade G1, G2, V for MZ, alpha, EM, and GF. And therefore, now predict all your observables in terms of MZ, alpha, EM, and GF instead of G2, G1, and V. And that you do that. So now all the observables that depend on MZ, alpha, EM, and GF very accurately measured. And I also will have a dependency on MF, namely MT, and also on MH, and of course, alpha S. Now, why does it have dependence on MT, MH, and alpha S? Because as I showed you, look here, the coupling, for example, of Z to FF bar pair is affected by this loop. That means it is affected by the fermion masses, and the largest, heaviest fermion will affect it most. So now you have, you do begin to have, for example, you can also have a Higgs here. So you can have dependency of your predicted observables actually on the masses of the missing particles. Now you calculate all the observables using one loop electroweak radiative corrections, and which, as I said, you could do in a renormalizable quantum field theory. And now you make a fit. You say these remaining parameters, what are the best fit values that are produced using the most accurately measured objects. And now you make a fit. So let me see here, show here. Let me give what is the meaning of the fit. So let's take alpha EM, MZ, and G mu as your input parameters, make a fit, and then find what is the fit value for MW. So the fit value of MW, which is from this plot, you can see here, is 80.385. This is the central value, and this is the sigma. So now what you see is that you compare, and sorry, the fit value is 80.377. I'm too early in the morning. Fit value is 80.377, and the measurement is 80.385. So you say, how much does the measurement differ from the fit? And the measured minus fit divided by the sigma of the measurement, which is 0.015. You see that for MW, the value, the deviation or the pull, as it is called, is less than 1 sigma. So actually, you see that after the fit, the pull for almost all the observable is less than 1 sigma. And as you have learned in your statistics class, that really means that it's a good fit. It's that is the hypothesis that the standard model is the right model, is indeed confirmed by this fit, except this forward-backward asymmetry, which has a pull which is about 3 sigma, and that had bothered people for a very long time. I will not have time to discuss this at all. But let me go back here. So now the values of alpha EM, G mu, and MZ that are used in this particular fit, I have taken them from the LEP working group on precision fits. And now you see that there is alpha EM, there is this G mu, and there is this MZ. So you say, okay, let me use the tree level relationship that I learned yesterday and calculate the value of the MW. So if you use value of G mu, alpha, and MZ here, you will find that MW is equal to 80.939. I will leave it to you to do that small exercise. But the experimental value, lo and behold, is 80.385. So now there will be the big deviation between 80.939 and the experimental measurement is 80.385. So this tells you that if we didn't include the loop corrections, we would have said that standard model is wrong by God knows how many standard deviations here. Okay? Because the difference between 9.3 and 3.8 is huge, and the error of measurement is 0.015. But lo and behold, once you take into account the loop corrections, and this is what was indeed done, this becomes 80.377, and that it completely and very happily agrees with this experimental measurement. So this is how, when you say that standard model predicts from the electroweak precision fits values of different parameters, these are these fit values. They refer to the central values of the fits. So standard model predicts this electroweak precision fits, predict 80.377 to be the W mass, and experimental measurement at that time was 80.385. So this is a very good, it agrees with standard model very accurately. So as I said, we calculate the loop corrections are calculated consistently in a renormalizable theory. I repeated that they can be they depend on the MH logarithmically, on MT quadratically. And what one does is one calculates measured values of MWMT, particularly those are the ones which are most critical, against those calculated from the electroweak precision fits for a large number of values of Higgs masses. And then you actually plot, let me, there is quite a few, okay. Then you actually, you can now see what is the goodness of the fit for different values of the image, that is, you calculate chi-square and calculate chi-square as a function of the Higgs mass. And this is what we are going to see in the next few transparencies after I finish the discussion of the next few slides. So this requires precision measurements and precision calculation. Then the LEP legacy was actually augmented by the tevatron precision measurement, because here this does not include the precision, very highly precise measurement of the MW, which came on the eve, almost on the, sorry, what happened? Somehow, 1 second. Can you people still see my screen?
Yes, we can.
Okay, good. Now something, there was a blip. So this LEP legacy was actually augmented by very precise measurements from first from the tevatron and now from the LHC, and maybe in future our ILC or FCC plus E minus, or if we get the click or CEPC, those E plus E minus machines could also do it. So what was the story in March 2011? Let me just show this to you. MW was 80.385 plus minus 0.015. This was the measurement. 80.377 GeV was the theory. MTOP was 173.20 plus minus 0.90 measured, and 172.26 was the theory. And in fact, way before 2011, in 2005 or so, before the top mass was accurately measured, actually even before, I forget the year when top was discovered, but I grew up in an area when top was, we constructed models without top. So I'm just forgetting the year right now. But the agreement between the measured and the prediction of the mass of the top was actually a great triumph for the standard model. And Weltman and Taub got the Nobel Prize only after that happened. And the Nobel Prize, I remember, was in somewhere around 1995 or 2000, something around that. Now, the current values of the MW and the MT are somewhat different. The tevatron and LHC have added to the precision. And now once the top was found and the predicted mass of the top was indeed agreeing with the measured mass of the top, now one said, okay, let's take this game forward. Let's take top as known and let's use make the fits, keeping MH, varying MH in this manner. And then let's see what produces the best fit. Where is the minimum chi-square of such a fit? And indeed, the value of chi-square at the minimum was actually not so small. So let me show you that in the next few slides. And people were bothered in July 2012. So before I go to that, I want to take a score sheet of standard model pre-July 2012. All of us know what happened in July 2012. So now that is why I'm focusing on what happened in 2011 and what happened pre-July 2012. So remember, what are the different things? The absence or suppression of flavor changing neutral currents told us that the quarks must come in isospin doublets. Just the charm was predicted, and top was expected to be present once B was found because of the absence of the FCNC, as well as because of the anomaly cancellations. Top mass and the charm mass were predicted from the measured size of the flavor changing neutral current processes, such as K0, K0 bar mixing or B0, B0 bar mixing. Some of you might actually be working on experiments which are measuring and studying the B0, B0 bar mixing. And recently, even the D0, D0 bar mixing is being studied at LHCb. And agreement with the experimentally measured values actually have proved that gauge theory of electroweak interactions is the right interaction. And you will study much more about this mixings in your flavor physics course. Then this is really what you will study, that the CP violation in the measurement system can be explained in terms of the standard model parameters and the measured CKM mixing in the quark sector. What we discussed today is that all the neutral current information actually could be explained in terms of a unique value of sin theta W, which gave us the prediction for MW and MZ, which was actually confirmed experimentally. MT was predicted from the precision measurement of MW and MZ, and that also agreed with the observed mass. So now experiments, theorists, particle physicists wanted to study, can we tell what the Higgs mass should be in the standard model? Because that was the point. And indeed, now I have fast forwarded to 2011, and I'm showing you the plot that I wanted to, I refer to all the time. This is just before the dawn of the Higgs discovery. And this is the blue area is actually the chi-square that I mentioned, that now make a fit to the standard model predictions, where you now vary image. And when you can make different types of fits, where you take MW and MT to be known, sometimes you let them float, and you do many things, and I will come to that in the second plot. But now the important thing in this particular plot, that you just try to vary image. And what you see is that the the minimum of the chi-square happened actually at the Higgs mass of 100 GeV. But LEP was also looking at hunting for the Higgs in the directly, that is E plus E minus going to ZH, and that was not observed at LEP. So LEP had entirely ruled out this value for the Higgs masses, and this was already done in 1992, and that was here 114 or 115 was the limit here. And then Tevatron actually kicked into the game, but Tevatron, being a P bar P machine, and was a, it didn't have as beautiful and clean environment as the E plus E minus machine, could look for the Higgs only if it was decaying into a one real W and one virtual W. So H going to WW star was the only channel that Tevatron could effectively hunt in. And Tevatron had already, by December 2011, and a little bit after that, had already ruled out these mass values, 160 GeV and more. So at this point, one said that consistent with electroweak precision testing and consistent with the non-observation in the direct searches of the Higgs by these two experiments, the Higgs mass should lie in the standard model in this small region if it has to be consistent with the electroweak precision measurement. So this was indirectly, you had seen that the Higgs mass should certainly be less than 160 GeV, and that is the point that came here from the electroweak precision measurement. This is just to show you how accurate the measurements already of MW and MTOF were. So here, this is the measurement of the MW and the MTOF. These are the direct measurements. And this line is actually the 95% contour for the prediction of the MW and MT from actually the precision measurement testing. And as you change the Higgs mass, I told you, you go on changing the Higgs mass, and you found that the Higgs mass is beginning from 114, which was the LEP excluded region, up to a Higgs mass of, as you can see, 300, and even up to 600. The electroweak precision tests were compatible, were allowing this region at 98% confidence, 95% confidence level. Now, in 2011, okay, already when LHC started, these, I had shown you this earlier plot. Now LHC started cutting into this white region, and it also started cutting into the heavier Higgses, because the Higgs which would decay into WW or decay into ZZ directly on shell was very easy to find, and LHC could rule that out rather simply. So these heavy masses of the Higgs were ruled out by LHC very simply. So now what happened? The blue area, of course, has remained the same. We really didn't have any new additional precision measurements of MW or MT in this small period. And the small period that is from this time to this time. And this white region was getting excluded by the LHC measurement. And really, this thin slither was all that was left in December 2011. So now here, this is the limits on where the Higgs should lie, such that in the standard model, all the precision measurements will be compatible with the standard model predictions, and it will be consistent with the non-observation in the direct searches. So this was overlap between direct and indirect searches for the Higgs. So before the observation of the signal at the LHC, the precision electroweak measurements had actually supported the idea that they like a light Higgs, that was this guy, because this chi-square going on increasing means that the larger values of the Higgs masses were not consistent with the electroweak precision measurements. So for the SM to be correct, Higgs had to be light, and and the direct observations had brought it down and excluded most of the region where the Higgs could be light. Now, before I go on and discuss now the actual observed value of the Higgs mass, let us ask the question, did theory have anything to say? So the direct limits were from explicit searches. The experimentalists were doing their great jobs and said, we did not find the Higgs. Because the good part of the theory was, of course, is that theory had predicted how the Higgs should couple to the gauge bosons, how the Higgs should couple to the fermions. Those were proportional to the masses. That was a very simple prediction, and therefore that's kind of helped the searches in the different final states, directed the searches in different final states. And the indirect limits actually used theory, but they needed the precision data to limit the Higgs mass. Did we have any pure theoretical limits which are arrived at by demanding theoretical consistency of the model? And this actually refers back to one of the questions that somebody had asked me in the end of the first lecture, that does the form of the vector scalar potential that has been assumed and loop corrections to that scalar potential, does that have anything to say about the theoretical consistency of the model as you change the one parameter in the theory, namely lambda, which has nothing to do with the rest of the parameters, but which is actually related to the Higgs mass? As we said, lambda was a free parameter. SM had no prediction for it. And you remember at tree level, the mass of the Higgs was simply given in terms of lambda and V. So can some theoretical considerations tell us something about allowed values of lambda and therefore the mass of the Higgs? And so far, I have discussed how indirect effects told us something about the Higgs mass. That is the precision testing. But what are the pure theoretical bounds? There are actually two types of theoretical bounds. One is actually considerations of unitarity of scattering amplitudes. Scattering amplitude of WW going to WW, E plus E minus going to WW, and nu bar going to WW. I will right now not discuss this much more. And the reasons are here, that the unitary considerations gave actually an upper bound for the Higgs boson mass, and our observed Higgs boson mass is way below that upper bound. So what is more relevant is the considerations which give a lower bound, and those are the considerations of stability. What is meant by stability? That here we have to understand the effect of the quantum corrections to the self-coupling lambda in the scalar potential. So now, instead of looking at quantum corrections to a Z going to FF bar coupling, I'm looking at the quantum corrections to the self-coupling lambda itself. That's also a field theory. I should be able to compute them, and indeed we can compute them. And the so-called triviality and stability bounds actually come by demanding that the quartic coupling lambda in this VH equal to lambda VH cube plus lambda by 4th H4, it should remain perturbative and positive. Now, this is a very mild theoretical limit demand, that since the mass of the Higgs is related to lambda, lambda should remain positive and lambda should be small, because otherwise this theory will become a strongly interacting theory and we can't even do perturbative calculations. So what are the things that come correct? So now actually the triviality bound come by demanding that lambda remains perturbative, and stability bounds come by demanding that lambda remains positive, and that the fact that the lambda should remain positive is obvious because the mass of the Higgs, as we have calculated, is dependent on lambda directly. So lambda and the potential will become unbounded if lambda becomes negative. So therefore, you better have lambda positive. So I will now show you the diagrams that give loop corrections to the Higgs. And for example, this is the self-coupling at the tree level. Then there are these corrections from the Higgs exchanges. Then there are corrections from the fermions. And then there are corrections from the gauge bosons. Now, if the fermion, if the Higgs is actually, if lambda is large, that is in the limit of large lambda, actually these corrections will dominate. So when I want to consider the triviality bounds, which I have few slides in, I will come to that if time permits me later. Then we will, for the large Higgs masses, actually it is these diagrams that are important. However, when lambda is small, then you must take into account these also, because G2 is known, and it's these couplings are proportional to G2 times mass of the fermion. These are proportional to G2 times mass of the vector boson, and you need to take these corrections into account. So when MH is small and lambda is not large, the fermion and gauge boson contributions are important. And what is interesting is that the fermion loops, I think basic rule of field theory, fermion loop comes with a negative sign, and the scalar loop or boson loop comes with a plus sign. So these two contributions to the lambda corrections are actually competing against each other. And this you can write down the rate of change of lambda as a function of log Q square, and that is called the renormalization group equation for lambda. This is actually the heart of the field theory, that in any field theory, any coupling will receive loop corrections, and in other words, it will run. And you are calculating the running of the coupling lambda, and the running of the coupling lambda, taking into account all these different diagrams, indeed actually is given by this small expression. Lambda square are the contributions of these diagrams. Then the lambda into lambda t square are the contributions of some of here you will have some w's, and you can get lambda into lambda t. So the Higgs is here, and you can get a lambda into lambda t square. And then there is this contribution, this loop is lambda t fourth, and this contribution is the lambda times G2 square plus G1 square. These are really the vector boson mixed diagrams of Higgs and vector boson, and these are the pure vector boson diagrams. And as promised, the loop contributions have minus signs for the fermion loops, and W loops have a plus sign. Lambda t is the Yukawa coupling for the top. At small mh and small lambda v, at some value of q, you can see here that lambda can actually turn negative because these contributions are becoming large. And if lambda is small, lambda t fourth is actually dominating everything, and the potential can become unbounded, and the vacuum will become unstable. Actually, this was something that was first shown by Linde and Weinberg. So you can actually solve this equation. It doesn't matter. It's an easy equation to solve. And you find that as long as mh square is greater than this quantity, then lambda will remain positive. Now, if we demand that lambda should remain positive up to a particular scale called lambda critical, because here this q is a variable, if we say, we say that, okay, lambda q becomes negative beyond lambda c, simply because there is new physics beyond standard model, beyond lambda c. And therefore, we will get a lower bound. So now if lambda c is 10 to the 3 GeV, you put that in this equation, you will find that mh should be greater than 70 GeV. So this is the lower limit on the Higgs mass you will get by demanding that lambda does not turn negative up to a particular energy scale. So if lambda should not turn negative all the way to Planck scale, then mh that you will get will be actually somewhat bigger. And these kind of calculations were done. And this was actually, I've taken this plot from a paper by John Ellis and Jan Judice, which was published in 2009. And this 2009 paper already had the tevatron exclusion that I have talked to you about, and already had the LEP exclusion. And what is plotted is mh versus the scale up to which we do not allow lambda to turn negative. And then you see that the Higgs mass will get a lower bound such that the lambda should not turn negative up to that particular scale. This is 10 to the 16, this is 10 to the 18. And here there are no more complications. You kind of try to see what is the absolute stability, how the stability will change if you do the analysis at finite temperature field theory. So this is now actually going into more details, which I again don't have time to discuss with you. But the point is that there is a lower limit, absolute stability bound that comes here. And here it says that if standard model is the only theory all the way up to the Planck scale, then the mass of the Higgs boson should be actually close to 130 GeV. And these are the upper triviality bounds, with basically saying that lambda should not become non-perturbative, should not become too large, and two different values of lambda, because what is large is an arbitrary choice. For lambda equal to pi and lambda equal to 2 pi, the demanding that lambda should not exceed 2 pi up to a scale of, say here, 10 to the 8 GeV, or up to the scale of 10 to the 4 GeV, tells you that the Higgs mass should be less than a certain number. In this case, for example, 340 GeV, if lambda should not become non-perturbative up to 10 to the 5 GeV. So these were the theoretical limits. Okay. So as I said that, because this rather closeness of this bound with this region, which was still allowed by the electroweak, because now I'm going to overlay on this. We have overlaid already in the earlier plot, the limits coming from the precision testing, and the precision testing had ruled out this entire region, right? Up to 160. So this whole thing was ruled out by precision testing. And then what was left was this really small slither that was at 2011, and this calculation was 2009, in fact. So now the closeness of this white region to this lower bound, the bound coming from this absolute stability, made people think that we should do actually a more accurate calculation. And that happened in 2011. But in 2009, this was the state-of-the-art calculation. And I have just taken this plot from 2011, which was presented by my friend Michael Kramer in one of the conferences. So what he simply did, he is overlaid on these theoretical bounds the results from the HC, from the Vettron by December 2011, from the precision testing, and from the LHC left exclusions. And what is left here is actually this small bound. And then you begin to see that December 2011, you were already seeing that even theoretically allowed regions, we were beginning to have a very narrow slither. So now we are from these two ends, and what I'm really trying to show you, that already in 2011, allowed Higgs mass range was restricted to a very narrow range from all these different constants. So the Higgs had not been discovered 10 years ago where it was. Perhaps it would have been more fun. But I think to the relief of all of us who had lived through the 4 decades from 1974 to 2014, LHC actually found the Higgs in that narrow slither and gave the final confirmation of the correctness of the model of leptons. And indeed, this was the reason why, in spite of only 10 events of Higgs to ZZ star going to 4 leptons observed in 2012 or reported in 2012, the Nobel Prize was already given in 2013 to Higgs and the other friends who predicted a Higgs-like boson. So this was a very famous plot which you would have been seeing now again and again. So this was a plot post-July 2012. I think this was very soon after that. And there is this MTOP measurement from Tevatron. And this is the MW measurement. And the MW measurement word average was this green band. This MTOP measurement, which was only kinetic measurement at that point. There are issues here. And again, I don't have time to discuss this. This is more a issue about how you extract MTOP from measurements. And there was, Martin here is a great expert in that, in fact. So here you have this band, green band. So these are the measured values of MTOP and MW at that point. And what are these different curves? That I will not have, again, don't have too much time to tell you what are all the different curves, but let me give you these these things, that this outermost gray curve is actually a 95% confidence level fit contour for the electroweak precision measurements that we discussed in great detail, where you did not use MW and MTOP measured values. You threw away those variables from your fits, and then you said, what is the range in which MW and MT should lie given the electroweak precision measurements? And indeed, it said that the MW and MTOP should lie in this big gray region, and depending on what the Higgs mass was, and the agreement of this central measured value with this, that was living inside this big gray region meant that the standard model has been tested and it is correct. Now, when the Higgs was found, you actually, made the fits, for example, here. So the gray region was without using MW and MT and MH measurements. But now the blue region was when I found the Higgs in 2012, July 2012. So let us use the measured value of the Higgs as an input in your fitting. And when you do that, you also basically fit MH. And what you see that the MH fitted value the MW and MT values should lie in this blue region, and the pale blue region and the measured region, that is this bar, lies, they have an overlap within error bars. And then you said this tells you that the standard model has been tested at one loop level, and standard model really rocks. In fact, as the years went by and MT measurement actually changed somewhat, and now you see, for example, the much better representation. So the directly measured values of the MW and M top should lie in this green region, and the MH value that has been measured. So now here you see three different kinds of fits. The gray is when you don't use MW, MT, and MH measurement. You throw away all the three measurements. That's the gray region. The green region is when you use the MW. The blue region is when you use the MW and the MT measurements, but you don't use the Higgs measurements. And that is what you see here as the blue. And the green region are the direct MW and MT measurements. So now you see that the blue region and the green region perfectly overlap at 95% confidence level. But already note that the MW, this is the still good old MW measured value, 80.385 plus minus 0.015. That is this central value with these errors. And then you still see that the direct measurement is a little bit above than the fit prediction, which is somewhat lower. So that was indeed the story, and that has been indeed the story. And this is the success story of the standard model. And that's why I showed you this plot at the beginning of my lecture as the proof for the standard model. Now, many of you have heard talks and have asked already questions in the discussions. So I will present this, that we do know that there has been a certain excitement that the MW, since these plots were made, actually there has been measurements, more accurate measurements, or different new measurements, I would like to call, and also with much less error, reporting much less error and reporting a quite different central value. So now you see that D0, CDF, and CDF2 are all actually reporting somewhat lower values of the Higgs mass, and rather somewhat higher values of the Higgs mass. But the important point of this latest CDF measurement was that its error was extremely small. And I don't have in this comparison the LHCb mass, which agrees more with the LEP measurement, but also has a largish error. So this is the standard model prediction, the 80.385 plus minus 0.015, because that is not going to change. My precision measurements have not changed and are not going to change. So this gray band is that 80.385 plus minus 0.015 GeV, and these are all the measurements. And now this is the big, this has caused some excitement. But in this case, I think this is, before deciding that this is a chink in the armor of the standard model, you really need to evaluate whether this precision that this new experimental result is quoting, that needs to be scrutinized. But I like this slide that Martin had made, and Martin, I am showing it to people here. So this is the same plot that I had here. And if the direct measurement was only the CDF measurement, okay, not fitted, this is not a fit, but only the CDF measurement, if you plotted it here, you actually saw that there will be a huge discrepancy. And that is the big difference between just the measured value. This is not a fit value, but this is what it would look like. So what this actually tells you, it gives you a good indication of how, what is the precision with which you have tested the standard model, and what is the precision to which you need to keep on making the measurements to be able to see some bit of room for non-standard physics here. That is the point that you want to see here, that the fact that this agrees with this so well is telling you that if there is space for new physics, BSM contributions, it's really tiny as far as we look at the current measurements. The CDF measurement seems to say that it sort of will throw it out of gear. But as I said, we really need to know whether this error is believable. So if the new measurement and its error should hold scrutiny, and the discrepancy with the standard model will continue, then what will be the possible reason? Can it be the missing higher orders in the calculation? I think that's unlikely, because the calculations are actually, the required accuracy is really there. Then the virtual effect, are there virtual effects of new particles and interactions? Are there tree-level effects of additional Higgses? And for the 2 and the 3 to be a viable solution, you will also have to be sure that you are consistent with non-observation of any new physics anywhere else. But before that, we'll have to wait and see if the error in the CDF result holds up, and indeed it is as small as it is reported. Because the error is large, believe you, then it will not affect the fit value too much. So this is the thing. So what have we learned? We have learned that just the mass of the Higgs actually can give us an indication of the scale of the new physics beyond standard model, and that is because of this. The difference between these two, is indeed telling us that the room for new physics is very, very small. For example, since I am a SUSY enthusiast and I've spent 15 years of my life working on supersymmetry and writing even a textbook on supersymmetry, let me tell you that the observed value of the Higgs mass, which is 125 GeV, is actually very close to the upper limit that the SUSY actually predicts, which is 135 GeV. And therefore, this already tells us that the masses of the SUSY's particles should be very large if SUSY is going to be relevant to particle physics. That is from the Higgs mass measurement. So therefore, in principle, nothing much wrong if we don't find SUSY at the LHC till now, because then the SUSY scale is expected to be large if the Higgs value, measured Higgs value, is any indication. Now you want to ask a different question, and that question is actually really indicated or inspired by this fact. Inspired by the fact that the observed mass of the Higgs is so close to this lower limit that theoretically was predicted from stability considerations. So the question one wants to ask is that, can we use the measured mass of the Higgs to actually ask the question and answer whether the standard model is all that there is up to the Planck scale, or is there something more? Can we see any footprints of the heavier masses or the new physics in terms of the gate structure or whatever have you in the masses and the properties of the two heaviest particles, Higgs and the top? And can these masses, can these couplings carry some message through the BSM? So that is one of the ways in which we try to proceed to look for BSM. That is why we measure physics so accurately, and that is where some discrepancies that we have in B physics we get excited about, because we are now looking at indirect effects of BSM on the properties that we are measuring very accurately, namely the Higgs and the top. Now, this is actually refers to the question that I was asked in the end of the first lecture, that, we are assuming this potential, and if you just plot that potential, then you find that it has the minimum at the Higgs mass. Now, if the Planck scale dynamics actually will destabilize the vacuum for more expectation value much bigger than the V, then in which case they might exist, this is the minimum where we are living, okay? But there might exist corrections which produce at high scales another minimum. That means that in the early universe, you could have had a lower minimum, and actually we may have settled into that minimum, and then if the vacuum has a very, very long lifetime compared to the lifetime of the universe, we might be actually sitting in this universe. This is, by the way, only a cartoon. I'm not drawing real effects here. So how do you calculate the transition rates from a deeper vacuum to the vacuum here? And this was something that Coleman had done. And these stability considerations, that is the meta-stability considerations, where had said, so this is really that you could lower the lower limit by making considerations. Let me go back to this slide. By making considerations of that the universe is only metastable and not completely stable, and then the lower limit could be lower. So if the Higgs actually had been found at a mass which was much lower than this lower limit, which was, for example, at 115 GeV, then we would have to actually conclude that either there is new physics at some scale, or we are living in a metastable vacuum. Right now, it's very amusing that the value of the Higgs mass that we have got and the value of the top mass that we have got is such that we are just about consistent with absolute stability. And this is this paper which you would have got, which you would have seen again many, many times. This is a paper called Fate of Vacuum and Mass of the Higgs. So here what they had done was that they had increased the accuracy of the calculations of the instability. There was a complete NNLO analysis, and this was really a major progress in theoretical calculations, such that the error on the upper limit as a function of the scale was actually reduced to about 1 GeV. So this is actually a plot from their paper, how lambda is changing as a function of the renormalization scale, and how you see where the scale, exactly the scale at which lambda turns negative, depends critically on what is the top mass. The top curve and the lower curve, the top mass actually changes between 171.0 and 175.3. So very small change. It also depends on alpha S critically, and whether your lambda will turn negative at 10 to the 8 GeV, or whether the lambda will turn negative at 10 to the 14 GeV. This is really dependent on what value of top mass you're using and what value of MZ are you using. So therefore, this is what we see. But this actually tells you that this is one way in which you can try to ask the questions whether the low energy measurements of the Higgs mass are indeed telling me something about the viability, the scale up to which standard model is the right picture. And indeed, this is again a plot from the same paper where they asked this question. Yes, I am now to my last few slides. Thank you. So this is really the picture of the top mass MT and the Higgs mass MH. This is the measured point. And what they did is they did the stability analysis over this entire MT-MH range. And what they show is that this region, this green region would have been when the vacuum was absolutely stable, but this yellow region is the region where there will be metastability, and this region is unstable. And indeed, you see that this measured value of MTOP and MH really seem to right at the edge. Now you will ask me the question, what is the scale up to which you are thinking of stability or instability? Don't think I have that plot, but there is a plot in that also about showing the scale. So, and that the point here is that this assumes stability all the way to the Planck scale. So, or 10 to the 5th, so maybe 10 to the 16, 10 to the 17 GeV. So what we are seeing is that the measured value of the top mass and the measured value of the Higgs mass are actually lying right on the where they should lie if we want the universe to be stable. And this then at this point the stability is up to all the way almost up to the Planck scale, and that's a puzzle why this is happening. So I did not discuss the upper limits on the MH earlier because, as I said, they are not interesting anymore as the observed Higgs is light and therefore weakly coupled. But when we didn't have any information on this theoretical, this is a wrong typo, this is a typo. When we did not have any information, I should put a comma here, the theoretical upper bounds actually served an extremely useful purpose, because the theoretical upper bounds, which I'm going to discuss in the next 3 slides, are indeed what actually set the target for LHC. Because when LHC target was defined and justified, one of the justification was that LHC project will be able to, should be designed such that it can look for the Higgs all the way up to the upper limits that are given by the standard model, various considerations in the standard model. So let me take a few minutes now to tell you how those upper limits are arrived at. One set of upper limits are arrived at by pure theoretical considerations and demanding that all these amplitudes, WW going to WW, WW going to, there are now 5 diagrams for WW going to WW. There is a 4-point coupling in standard model for WW. Then there is this T-channel exchange of the Z and the gamma, S-channel exchange of the Z of the gamma, and the T-channel exchange of the Higgs. Okay. Now, each of these diagrams, if you compute, easily done, it has a very bad high energy behavior, and the cross-section rise like S to the power alpha. Sometimes alpha is 1, sometimes alpha is 2. And this is a very bad violation of unitarity. And I have already referred to the unitarity violation for the cross-sections. This is even worse than that. And this is really coming from the longitudinal degrees of freedom of the W. And that is giving rise to this bad high energy behavior. But what happens is that all this bad high energy behavior actually cancel among all these diagrams, and the net result of the amplitude, when you sum over all the contributions, actually the bad terms cancel, only a logarithmic dependency on S that is left. And this happens only if the Higgs couples to the W with a coupling proportional to the mass of the W, and the ZZW coupling is exactly what the standard model SU12 cross U1 gate structure has. Then only these actually cancel with each other. And therefore, this is actually what I wanted to say, that in let me complete right now. So this is the reason that this is one of the stories in the standard model. So now what Thacker and Lee, again the same Benjamin Lee that I referred to earlier, he actually had a very untimely death when he was young. So Benjamin Lee, again with Quigg and Thacker, saw that, yes, let me look at this a little bit more, because these couplings of the ZWW in the SU12 cross U1Y and the Higgs couplings to the WW are what are predicted by the gauge structure and by demanding the renormalizability. So maybe, there is a connection between unitarity and renormalizability. So what he noticed, and what these 3 authors noticed, is that if you look at this WW going to WW scattering amplitude, you calculate the sum of all the amplitudes, then you find that there is a leftover MH dependent piece. It's no longer diverging, but it depends on the Higgs mass. And now if you say that this should not rise with S, indeed you find that you try to calculate at what energy will this amplitude violate unitarity, and you find that it violates unitarity for the Higgs mass when the Higgs mass is very large, and that is about 1000 GeV. Now they did a more correct calculation, keeping the logarithmic terms also, and then they found that therefore, if this indeed has to not violate unitarity at any energy, then the Higgs mass should be less than 780 GeV. So this was the upper limit from unitarity considerations. I also told you that at large MH and large lambda, the loop corrections were for the lambda were actually dominated by the scalar loops, And remember, mh square was lambda v square. So now at one loop learning, throwing away all the W and the top contributions, this is the simplest one loop running, keeping only the scalar contributions. You solve this. So here you have dropped all the other corrections to the self-coupling because lambda is large. And now you solve it and you find that actually this would blow up at a certain value of q square when the denominator vanishes, but the scale at which it will vanish will be dependent on the value of lambda at a lower scale v square, and lambda at v square is our Higgs mass, measured Higgs mass. So therefore you say that you ask the question and you demand that this scale at which lambda will blow up. Now, instead of becoming lambda negative, lambda should not blow up. So you ask this question, what that up to a given scale, lambda c, v capital lambda c, you say that lambda q square should not develop a pole up to that lambda c. So if you ask that question, that demand that the scale at which lambda blows up is above a given scale lambda c, then you can calculate for a given Higgs mass, that scale. And if lambda c is equal to lambda is equal to 10 to the 60 GeV, we find that a Higgs mass should be less than 200 GeV. So if the observed Higgs mass would have been already beyond 200 GeV, then we would have said that, aha, this tells us that standard model breaks down at 10 to the 16 GeV. So this upper bound is called the triviality bound. And why this is triviality bound? Because if lambda has to remain in the perturbative regime, then in principle, from strictly speaking, from this region, you will see that the only correct solution is lambda equal to 0. And that means theory is trivial and it will not do anything for us. So therefore, the fact that the pole is lying above a given scale lambda means that the Higgs, if the Higgs mass is less than 200 GeV, then the theory does not become trivial. So just the mass of the image can actually now give us an indication of the scale of new physics beyond image. So indeed, what now we see is, I just wanted to bring these bounds to you because that's what went into design of LHC. But as I correctly said, for the observed mass of the Higgs, indeed, that is, those limits are completely irrelevant now. And the real question is, can we use this to understand? And people are discussing very sort of heatedly whether there are some cosmological considerations which can tell us something about what the standard model does at the high scale from this value of the Higgs. I don't know any of the concrete results, but this is an area where some of the theoretical physicists spend quite some time, but that's where we are. And these are the three chinks in the armor of the standard model. One is the G-2 of the muon, one is the flavor non-universality, and one is the precision measurement of the mass of the W. I'm sure you're going to discuss a lot about this lepton flavor universality violation in your flavor physics course. That is something one direction, because in the standard model, flavor universality is almost there by construction. So if you do observe flavor non-universality, there is no little bit of corrections in the standard model that will explain that flavor non-universality. Therefore, that's a very qualitatively new aspect and deserves full attention of the theoretical and experimental community. Then the G-2,
in a couple of minutes?
Actually just the last two slides now. So the difference between the theoretical expectation of the standard model and the measured value for the G-2, it at the level of 1 part per billion. But indeed, this is perhaps evidence which seems to be very, new physics seems to be compelling, but you need a critical evaluation of the theory prediction. And here we need the knowledge of QCD at very small scales. So that's but again, there are interesting interplays between precision measurements and these discrepancies, but that is something that some people are investigating. So I think I have already discussed the last one, namely the MW discrepancy. So I say that the days of standard models are coming to an end in some sense. We are hoping that it is the case of the king is dead, long live the king. I have said that already the mass of the Higgs may be used to answer the question about the scale up to which the SM is valid. The answer seems to be that it could be valid all the way to Planck scale, but It need not. And just like the gauge principle and the unitarity, where the guiding principles through the 3 lectures, which I tried to point out to you in the development of the standard model, maybe now the lightness of the mass of the Higgs is really the guiding principle for our future developments. And maybe we will get a peek at the BSM land through the window of the measurement of the properties of the Higgs and the top, which is what many of you are interested in and working on. So all I can say is that if 14 TeV, if LHC, even with high luminosity run, doesn't find any direct evidence for the BSM physics, we really have to understand what is so special about the standard model. And we really hope that the answer won't be anthropic principles. So it is this window of the Higgs and the top that we are going to look through at the BSM land. And as far as theoretical physicists are concerned, we are, many theoretical physicists are actually seeing whether the Lagrangian that I showed you on the back of the t-shirt in the first slide, maybe now they are seeing how the Lagrangian can be enhanced to also add gravitation and also add the theta term, which some of my friends were asking me questions in the discussion sessions. So how do we develop a quantum theory of gravitation? And do we have understanding of such things such as the strong sector CP violation? These are the questions. Why is the Higgs mass it is? Does it give us any hints about non-Planckian, trans-Planckian effects? So on and so forth. So I think it's a very exciting life, even beyond the standard model. So I think it is the story of the king is dead, long live the king. Thank you very much. That is for your patience and for giving me the extra 3 minutes, Suchita. Thanks.
Thank you very much, Rohini, for this very nice set of lectures.